Okay, are we ready? Okay. Thank you for bearing with us on this delightful container track today. This is the last session. Shouldn't be too long. Just a reminder that immediately following this is the happy hour, so it'll be from 4:45 to 6. This session conveniently gets out right at 4:45. So be first or be beerless. So I guess just push and shove out the door like usual. So this is advanced container scheduling and resource management. It is not as boring as it sounds, although I successfully scared away enough people for everyone to have a chair this time, so everyone is welcome. It'll be a little bit more of an assortment of things, though. So we'll talk about resource scheduling and some different ways that you can do that, some ways that you can get more out of scheduling your containers themselves. And we'll talk about some of the things that let us do that, and then we'll look into some of the internals on how we actually handle the scheduling part and how you can customize that if you so choose. So first things first, what is container scheduling and why should you care about it? So scheduling is just how your containers are placed and run. So that might be something that, how did you schedule that container in response? So like to an event or based on a cron expression or as part of a long-running service. Could also mean something like task placement, which we'll dig into. So just like with kind of the overarching managing of containers with Fargate, managing one container is really easy, and managing many containers is hard. So there's many pieces, all with very unique resource requirements. A lot of them can run in response to different events or different tasks. So it's really an area that, although you do not need to customize, you can get a significant amount of resource usage improvements and performance improvements out of customizing a little bit. So as always, the default is totally fine. So for everything that we're going to talk about today, there is a default. So for task scheduling, there's a default. For placement, there's a default. For the resource usage, there's defaults. So if you're not ready to dive into any of this, that is totally fine. Trust the default, and you can add some of this as you get along. So starting a little bit with the scheduling part, a couple different components that we'll look into. So the scheduling engine, the placement engine, and extensions. First one up is types of schedulers, so the scheduling engine. So a couple different ways, and this is more commonly known for a lot of people as what kind of job it is. So something that's managed by a service is like a service job. So an ECS or a Fargate, it would be like messaging service or something, and it controls, okay, I want a minimum of 4 tasks, a desired count of 6, and a maximum count of 45. So that might be an example of a service scheduler. The service is responsible for starting, restarting, and stopping those tasks. You can run batch jobs. So there's some really cool architectures out there that do batch processing with ECS. So to take multiple items off a queue or something like that, process them all in parallel, and dump the results somewhere else. You can also have event-driven. So some questions earlier about how to run cron basically in a container. This is a closer equivalent of that, so more kind of container native way to do it. So you can do it in response to a cron expression, or you can do an event-driven one. So that might be something like a CloudWatch alarm. You can also do daemon processes. So an example of that might be like a logging agent or a monitoring agent, something that you, in a past life, might have run on the EC2 host itself. So you run one of them, it hangs out collecting data from another container or another process. Placement engine, so there is a default behavior here, which I'll get into in a second, but the task placement engine basically tells you how you can place your tasks among your pool of resources. So you can filter on custom things, so on a certain AMI or an availability zone, or a custom one. So if you label your instances with the key value pair, so like in this case stack is prod, you can place based on those characteristics. You go a couple different ways here. So the first one is cluster constraints, which we're going to dig into. So a cluster constraint is, does it have the hard number of resources that it needs to support that task? So does it have CPU, memory, and in some cases, does it have port? Port is a hard constraint, but we'll talk in a second about how with some of the load balancer types, port is no longer a hard constraint. But for the kind of classic way of looking at things, you have kind of 3 big ones. And there are more resource constraints other than that. but port, memory, and CPU. Then you have custom constraints. So these are the ones that we just looked at. So does it meet my strategy? So like a bin packing or a spread or distinct instances. Does it meet my strategy? So something like filtering an AMI ID. And then finally select the final instance for placement. So some supported placement strategies. So this is what we were talking about a little bit earlier, and people are making, obviously, jokes on Twitter about the room being bin packed earlier. Bin packing means fitting as many containers as possible in the smallest amount of space. So that I use, if I have 2 available instances, I will fill one instance as close as possible to full before allocating my tasks to a new instance. So this is really good if you want to. Well, one example is really good for like a development environment where you want to put the least amount of resources towards running your development environment. So you want to pack in as many tasks as possible before scaling up your pool. People do this in production too. So I use Segmented as an example this morning where they use bin packing in production to run as many events as possible. I'll get into it in a bit, but you can use these strategies in conjunction with constraints also. So you could, for example, bin pack while distributing between availability zones. You also have spread, which will distribute your tasks as evenly as possible between the instances that will support the tasks. You have affinity, which means go in like groups. So if I have task A and task B, and they belong together, the placement engine will always put task A and task B together, and we'll keep them in pairs like that. Distinct instance. Try to keep one copy of that task on every instance that's running in your cluster. So if I have one on 2 of the instances that are running and I have one that's empty, fill that empty one before moving on to another instance. You can chain these though. So if I wanted to spread across zone and then bin pack within that, I can add multiple strategies. So I could do distinct instance within spread. So spread as much as possible, but make sure that they're on distinct instances. I could do it by affinity. I think the most common one, though, is probably bin packing while also spreading by availability zone. So still keep high availability, but use my infrastructure as kind of tightly as possible beyond that. So who's responsible for all of this? Because sometimes it's you, and sometimes it's not. So container manager is in charge of basically resource management. So how many resources do you have available? How do I know when a resource has changed? When a service requests resources, how do I allocate that? And it's in charge of making sure that all those numbers match up. So if you didn't have a container manager, you'd run into an issue where a service requested resources, got resources, so then you were missing resources from the instance, and then another service tried to place a task there and thought that it had enough, but since there'd be no updates, it wouldn't be able to place a task there, but it wouldn't know until it tried and failed. So a container manager is in charge of keeping all of that straight. So how many resources are left in the instances, where there are resources left, and then keeping track of accepting or denying requests for resources. Resource constraints. So I said CPU and memory and ports. You obviously have a couple more, things like network bandwidth and IOPS and disk space. So these are all resource constraints, meaning with some exceptions, you cannot get more of them without changing your instance type. So if I need 1024 of CPU to deploy my task, bless you, to deploy my task, and the box that I'm trying to deploy to does not have 1024 of CPU, I cannot deploy there. That is a resource constraint, and I cannot make more CPU on that box without either redistributing the tasks that are on there or trying to deploy to a different instance. So they're hard constraints or semi-hard constraints. They're the first things that need to happen on your order of operations. So it's a lot like middle school math class, where you have to go in the order and you have to evaluate them in order. So the first one for placing your tasks is always going to be those resource constraints. So does this server physically have enough resources to support my service? So what enforces this? So in most cases, this is going to be the ECS agent in their container manager, right? So on that instance, I'm running Docker. I have my tasks. I have the container that belongs to that task. And it's the ECS agent that's responsible for all of this communication. So If you've ever gone in and looked on one of your boxes running on ECS, the ECS optimized AMI sets up that agent for you, but it's responsible for doing all of that communication. So communicating back to the state manager, accepting the resource requests, and then whether the task has started or stopped, so whether it's been able to fulfill the request. And we'll look at a timeline of how a request goes through those different managers. A quick digression, though, to talk about load balancers, because they have an impact on how you can schedule and use your resources. What's a load balancer? High level, they distribute your traffic between targets. So that might be between IP addresses or containers or tasks or EC2 instances. So different types of these. Started off with ELB Classic. So that's the original. It balances traffic between only EC2 instances. That's it. Right now, it's pretty much designed still for EC2 Classic. So if you're starting up new services or you're working with ECS, the strong suggestion is you go with application load balancer or network load balancer. Had a couple of really interesting questions on these after the State of the Union about how do you know which one is good for you. I included a link for when you're looking at the slides. The load balancing page is very thorough, and it will give you a whole list of the different use cases and when is good for one. I put in a couple of tips. Application load balancer, I think, is extra great for microservices because I can route based on path or content. So rather than having one load balancer per service, I can have one load balancer with multiple target groups that will distribute the traffic. So it lets me use my top-level resources a little bit more effectively also, because instead of having to have 25 load balancers for 25 services, I can have one load balancer with those 25 target groups that all route based on path. So a path in this case might be something like /web or /API or /friends /v1. So I can route based on that way through the load balancer. Only VPC. Network load balancer. The big thing for me on this one is you get a lot of questions still about pre-warming load balancers. That's something that you don't have to think about for Fargate, but it's a pretty traditional question for Elastic load balancers, that there used to be some cases that you'd have to contact support and ask them to pre-warm your load balancer when you were switching your traffic over. Network load balancer is designed to be really high throughput, really low latency. I can't spell throughput, by the way, so if for some reason that's not how you spell it, then you know what I mean. Spelling is hard. So where I think this is really good, though, is for people that have a really erratic use case. So if you're one of the people that has no traffic and then jumps up in the number of requests per second, but then it goes back down again and then jumps back up, goes up a little bit, goes down a little bit, goes back up. So that's before, it would have been a really hard traffic pattern for a load balancer. So if you were switching your load balancer, you'd have to have it pre-warned because it wouldn't be able to keep up with the sudden influx of requests. Network load balancer is great for that. You can also use it to assign an Elastic IP per subnet. If you're looking to switch your load balancer type, I very much recommend looking at that breakdown page because it will give you more information than I'm going to do. What does it have to do with scheduling, though? So first, that's what's in charge of actually distributing your requests. So your load balancer is playing a pretty significant role in your scheduling to start with. You can also do, I think, little known tip for speeding up your deployments with ECS is that a lot of these things can still be controlled at the load balancer level. So for example, connection draining. Connection draining is the time period that it takes for the load balancer to gracefully start allowing connections to wrap up before draining them and then replacing them somewhere else. So an example of this would be in an ECS deployment, that when you add a new revision of your task, the load balancer will very, very, very slowly drain connections off the previous revision if it passes health checks, and then we'll roll those over to the next revision. That's an example of connection draining, and that's something that you can speed up by tweaking this connection draining timeout. So by default, it is quite generous, but if you don't need that much time, you can shorten it, and you can drain connections off a little bit faster if you don't mind that every once in a while someone might get briefly disconnected and then reconnected. Not good if you're doing something like WebSockets, obviously, but that's why you have a WebSocket, is to connect to the WebSocket. So Highly recommend looking into those load balancer settings because since they're not accessible through the ECS console, they're often overlooked with how to speed up your deployment. Another cool one is the auto scaling group cooldown period is often very generous. And a cooldown period is the time that it takes to sit and do nothing before it reevaluates the auto scaling rule. So in some cases, you might auto scale and add one instance in response to changes in cluster resources, and then wait n seconds, so 300 or something, before it will reevaluate the rule again. But for a lot of people, that doesn't help them then add more resources more quickly if their pattern was changing more dramatically. So you can tweak things like the cooldown period to allocate your resources a little bit more efficiently and a little bit more quickly. Secondly, dynamic port allocation. So this is kind of the original way that you were able to do that. So previously with ELB Classic, you had to bind always a container port to the host port. So port 80 on the container was mapped to 8081 on the host or something like that. But guess how many copies of port 8081 are on each server? There's only one. So it is very much a hard constraint. And that was really limiting for a lot of people because in order to run, and especially with monoliths, right, it's because in order to run multiple copies of your application and scale up, you needed a whole other server. And if you're using dynamic port allocation, you can bind it to port 0, and the load balancer will take care of allocating a port for that service to run on. So theoretically, a service that used to only be able to run one copy per host can now run many copies per host with port allocation happening at the load balancer level. We talked about AWS VPC earlier. Do you see Paul with the stand microphone? My assistant. Paul. OK, I'll repeat your question then.
Yeah. Okay.
Yeah.
So my question is, how would you manage SSL if you define dynamic port on the container level? I know you can do it at the application load balancer level, but if I want to do HTTPS on my container level, then how do you do that?
So HTTP and HTTPS can happen through ALB. How you do, oh, sorry, I'm repeating the question, which I didn't do a good job of. So repeating the question is, how do I manage things like SSL with the load balancer when I'm doing dynamic port allocation? In a lot of cases, SSL terminates at the load balancer. So your SSL connection is from the client to the load balancer, and then the connection from the load balancer to the container is not always SSL. In some cases, it is. If you're doing WebSockets or something like if you're trying to do like socket connections, everyone has a different, potentially extraordinarily hacky way of doing it. I used to also do it a very hacky way, so don't ask me on Twitch, but I'll tell you afterwards. So different people have different solutions to that one. In a lot of cases, I've just terminated it at the load balancer. If my lovely assistant ever rejoins us, perhaps he has a good answer as well. I don't know where he went, though. He totally abandoned me after I did questions for all of his talks. So he's not going to get a beer if I find them. OK. So dynamic port allocation. A big win, I think, that doesn't sound that exciting. But what it does let you do is use your actual cluster resources in a way that's significantly more efficient. So in a lot of cases, you can use way less instances than you could before. So if your cluster is full of like C4 triple XLs, like adding one less of those is a big deal. So use your resources just a little bit more effectively. Use what you have. Going to talk a little bit about the importance of images. Oh, we have beers. No Paul, but we do have beers. So if Paul comes back, tell him he can't have a beer. So the importance of images here. So I think this is one it's also a hot topic, or a lot of people have. I get a lot of emails about people that are having issues with this. A huge way to eat up all of the disk space, not that I'm speaking from experience, and get paged is to not control the size of your Docker images at all. That's how you can, especially if you have auto-scaling rules, they'll just keep adding hosts to your cluster. And you're like, well, when I left yesterday, there was only 10. And now there's 15. And also, I'm getting paged saying that you're running out of disk space. So don't be like me. Definitely watch the size of your Docker images. They add up really quickly. In general, and this is only sort of true with Docker 1.1, someone asked a question and you weren't here. Yeah, you're not allowed to have one. In general, it's a little bit different with Docker 1.1, but the more layers you have and the larger those layers are, the larger your final image would be. So obviously that eats up disk space. A couple ways that you can make this a little bit better on yourself. The first one, which is only on this intro slide because it didn't fit in another slide, you don't always need the recommended packages. So an example from apt-get, no install recommends. Every time I use that example, someone says, but in my package manager, it's this. I know that there are other package managers. I only included one on the slide. Please insert in your head the appropriate no install recommends command for your favorite package manager. So how can you reduce image size? So something that we didn't talk about earlier that maybe we should have is using shared base images. So I get a lot of questions on, well, how can I use up less space for my images? It's a Simpsons quote. It says, shrink Ray, well, there's always something else to buy. So use your shared base images where possible. So especially if you have 5 services that are all written in Node.js, maybe you want to share a Node.js base image with the common packages, and then only your app code is different on top of that. Limit the data that you write during the actual execution of your container to that write layer. So containers are basically a stack. So it's the base OS and the read-only that forms the base of the container. Then there's a really thin read-write layer on top of that. So limit the data that you write during that execution phase. So something like adding a large file. You can chain your run statements. So something that I would have done when I first started out with Docker would ordering every line, and I'm sure it looked beautiful, and I'm sure I commented everything, but it's like apt-get, update, comment, apt-get, install, and then I installed a bunch of stuff. And then I cleaned up, and then I did something else. And although that looks beautiful and readable, it is not super effective for caching purposes. So chain your run statements. There's lots of blog posts about this if you're looking to learn more. But in general, also just prevent cache misses at build for as long as possible. So let's talk cache for a little bit. Docker has all kinds of exceptions, by the way, to how they use the cache. I put a link in a couple of slides from now to their documentation on the exact order of operations they use for their cache. But at a high level, run, add, and copy all add layers. Starting in Docker 1.1, other instructions do not do that. If you are on a different version of Docker, other commands also add layers to the final image size. Really, really, really quick overview of how the cache works. Starting from your current layer, Docker looks at all subsequent layers to see if they use the exact same instruction, and I'll explain that. If they match the exact same instruction, the cache is used. If you're adding or copying files, it checks a checksum. Other than add and copy, the contents is never checked. So like apt-get update, that string has not changed, so it will use the cache. So sometimes, this is my footnote, so what happens if your command string is always the same, but you need to rerun the command? So a good example of that is pulling from a Git repository. The repository address of your registry will never change. So a lot of people do something by either passing the flag to ignore the cache entirely, or you can cache break by adding something like a different string every time. So for a lot of people, that's a timestamp, so that they change you're effectively changing the line every time, so that it's forced to rerun the command, even though the string that makes up the command has not actually changed. Clean up as you go, obviously. If you install a big tarred file, delete the tarred version in that same line. Anything that you do within the same line, within the same instruction, does not commit to the final image size, only the result. So if I install, unzip, use, and then delete the tarred version, that tarred version of the file will never be added to my final image size, just the contents of that file that I used for something else. Do built-ins also. So every single package manager has something about either removing library files or purge or something like that. Clean up after yourself. The same thing with your local machine or on that system. So you can prune images or you can prune the system, which will get rid of dangling volumes. So with containers comes a little bit of a mess. So clean up after yourself. There is a garbage collection as part of most orchestration tools. So there's one in ECS or Kubernetes. A lot of people say that the built-in does not quite get them the amount of cleanliness that they would like. So there are third-party ones out there. One that I've used and liked that's open source is Spotify GC, which is a collector container that will basically run on your host to clean up more aggressively unused images. Something else that I've done to save images in the past, to save space in the past also, is if I'm running a log collection container anyway, I very aggressively log rotated things away. Because disk space, as exciting as it sounds, disk space is a resource too. So you can have the most advanced task placement policies and strategies, and you can write all these complicated things, but if you run out of disk space, you still have a problem. So be responsible with your Docker images and with your layers. I promised a little bit of a timeline on how the internal scheduler actually works. So when you launch an instance and it registers itself with the ECS cluster, it reports its total amount of resources. So it calls it as total resources. So it'll report every single thing unless you tell it not to. And that gets added to the whole pool. So that way the agent knows, OK, so between this whole pool, I have X amount of CPU and X amount of memory available. You can modify that, so you can hide things from the ECS agent. So if you have resources that you want to use for like a daemon process or something that's not managed by ECS, you can hide resources from ECS, so it won't try to schedule on top of that. It works for memory, ports. So you can pass that flag to the agent so that it doesn't try to steal your resources. How do accepting resource requests work? So for a task, it starts with a request. So the task says, are there available resources in this pool for me to run? And if there are, it looks for container resources and for the task resources. So we've talked about those before, but you have the hard ones and the soft ones. So what does my whole task need, and then what does this individual container need? Your regional cluster management engine, you send it that request, and it either approves it or rejects it. And then the cluster management engine does it within availability zone. So if you lose availability zone, you can continue to schedule to your cluster, but to a different availability zone. Once the regional engine has approved the request, it sends it down to agent communication that you need to change the state of a node. So you go from your regional cluster management engine to the agent communication engine. Agent communication service pushes that down to the individual ECS agents. So from regional management to agent communication to the ECS agent, which belongs on all those nodes. So if you've ever looked in the ECS console before, every instance has its own copy of the ECS agent that the ECS optimized AMI starts for you, and that if that ECS agent is no longer registered, you can't schedule to that instance anymore. Once that request has been sent, our service will acknowledge that it either performed or did not perform the update. So stopping a task, starting a task, restarting it. The task is now running, so how do we keep in sync? That's by your regional engine. So requests, so we talked about how our cluster manager keeps track of the state changes, bless you, and resource requests. So you keep track of all of that, and that's responsible for taking the inbound requests from different services, so it knows how many resources are left in the pool, and that's how you'd maybe know at some point, I need to scale my cluster up. So how could you do this either from the CLI or write something yourself? So you can use something called cluster query language, which will return things that match your filter. So in this example, it's an ECS demo, and it will return everything that matches the instance type T2, but anything in the T2 family. You can also match just a specific type. You can match on multiple attributes. So I can basically use this query language to do anything that I want to do against my pool of resources. So see how many are available. And this is under the hood how you would end up writing a task placement policy yourself. Is what do I have left that matches this expression? Is it enough to run my task? I can chain those obviously. Couple examples. So in this one, I can go via availability zone that's not US East 1D. Oops. I tried to make purple dots that flew everywhere, and I don't think I've really quite figured out the whole PowerPoint animation situation because they kind of just moved in a big chunk. But But this is an example of bin packing and then within availability zone. So I'm spreading them between availability zones, but then I'm bin packing within that. So using my resources as effectively as possible, but still spreading it across availability zone and then also on memory. Can do distinct instance. One caveat is that distinct instance does not quite work the same way that, that one per host. The traditional, I think, idea of one per host is that I run one copy of this task and only one on every single instance that's a part of this group. And I think it does kind of work like that. It does not always work as intended, I think, for auto-scaling. So it works when you're actually deploying the task, but I do not believe it will currently account for auto-scaling. So when a new instance comes up, it does not automatically start a new copy of that task. You can do this from the console. So if you want to get started with placement, the default is this AZ balance spread. So spread as evenly as possible between all the availability zones that my cluster is running in. You can choose not to change anything. It will just default to this, and it will work quite well like this. There's a couple templates to help you get started, or you could write a custom one. You don't have to write cluster query expressions to do this. You can do the dropdowns. So this one would spread on availability zone, then by instance ID, and then by memory. Scheduling for containers, just like your calendar. I don't dry clean anything, though, so this is obviously not my calendar. Two different ways I think that are important for looking at the task scheduling. So the first one is load. So what does that mean in real life? That's how would I run a task in response to something like a CloudWatch alarm. So my CPU exceeds a threshold. I know that there's a typo in here before anyone points it out. If it exceeds a certain CPU threshold, or if it exceeds the number of memory or the number of messages in a queue, scale up either by a couple instances or just by one. And then obviously you have to have the opposite too. So don't just keep scaling up until infinity. Have the inverse of that rule too, so that if your CPU goes down below a certain threshold, remove instances. So this is the cron kind of ones that I was talking about earlier. I can run tasks in response to other things like a specific time or a cron expression. So although you do not typically run actual cron inside the containers, you can do it like this. So run the action in the container based on either the evaluation of the cron expression or a specific time. So I will take questions now if anyone has them. Maybe Paul will play with us, but maybe not. Yeah.
When it's resource constrained, so you gave the example.
Sorry.
When it's resource constrained, you gave the example of CPU. Is it possible, if there's enough overall in the pool, to shuffle instances off onto another host and drop the container on there?
Not current. Oh, so the question was, because I think we started with the microphone halfway through, is it possible to rebalance tasks? So if your pool has a sufficient CPU, but the only instance matching the constraints does not have enough CPU, will ECS rebalance? Currently, no. I believe that there are enough events exposed. Oh yeah, you get a beer if you ask a question. So start thinking of exciting questions.
Yeah, now you get your hands up.
Yeah, now everyone's excited. This is the fun track. Not right now. ECS exposes a ton of events. So I feel like it must be, you could kind of do it yourself, but you'd have to pull for a lot of information, and it's not native right now. But I would love to see it.
I've seen a few open source projects. In fact, I think there's one on Nathan Peck's repo that does a Lambda event-based reshuffling, rebalancing on the cluster. It's not built in at the moment to do that.
By the way, and I said this to people in between, but if you have specific ideas or requests like that, definitely email or tweet or DM or use the AWS wishlist hashtag, because we do actually look at them. And actually every time someone sends me a feature request in my email or on Twitter, I copy and paste it and I send it to the person in charge of that team, which I'm sure he's enjoying. But
sorry,
I think it's a good way to share
feedback. Cameraman reminded me I had to stand next to you when we were answering questions. Sorry, cameraman. And for Twitch people, I'm not drinking a beer while working. These are for customers, honest.
Gray shirt, yeah. Now it's Paul's turn.
Did you want a bit?
No, but I can give it to him.
This looks like
I
beer
don't drink.
delegation.
Sorry. So the question is how the balancing would work in relation with bridge or host networking.
I'm not sure I follow the question. So
So-
the networking type shouldn't have a huge impact on how you're allocating resources. The network type, to me, determines how those containers communicate with each other.
Okay, let me rephrase the question
Okay.
then. So let's say I have a container, which is container type A, and let's say I would like to run 2 tasks, and in my auto-scaling group EC2 auto-scaling group, I have, let's say 1 instance, although I would like to get more. So that means that 2 container of similar type needs to run on the same host. So if I use host mode network or bridge network, then how the balancing is going to work if I do not define dynamic port?
I think Paul wants to answer.
Yeah, so if the scheduler within ECS needs to schedule 2 containers onto a host, and you are using a mode whereby you can only have 1 on that host. So for example, with host-based networking, if they're using the same port, like port 80, obviously there's only 1 port 80 on the box, you're only going to get 1 running on the box. ECS will fail to schedule the other one. So that would be a good case for when you have auto-scaling to scale up your requirements. Ideally, though, you want to get away from the idea of locking into individual ports. So use a network mode like AWS VPC, whereby actually the host port doesn't matter anymore because each task gets its own ENI.
Well, and the port is considered a resource constraint. So if you're running something where it is bound to a specific port, the scheduler respects that because it's technically a constraint.
Following that question, so basically we have a use case where we need to do the SSL termination even on the container level. So that means we are running .NET Core application under the Crystal, but on top of that we use NGINX to do the SSL termination. But if you do so, then that means you need to occupy port 443, and which is the host port. Then actually the balancing of the task doesn't work.
At that point, if you have hard requirements for if something must run on 443, for example, then use the AWS VPC networking mode or something whereby each task will get its own 443, basically, even on the same host, because there's multiple ENIs, multiple IP addresses. Each one of them will have their own 443. If you don't use that networking mode, with SSL termination not on the balancer, with it in the container, I think that's going to be your main option. Or use a dynamic randomly allocated port and use something like DNS-based service discovery for that. Like console or Route 53 or something. So a common pattern is to use the Lambda function that listens to the event stream on ECS. When a container comes up, it registers it in DNS in Route 53. But that is going to be integrated into ECS natively very soon. So, yes, sir. Did you want a beer?
One of the issues we had when we wanted to do auto-scaling using ECS was that we couldn't figure out a way of configuring auto-scaling for EC2 and ECS at the same time. So we ended up having we just told ECS to run 20 applications, but it kept failing because it couldn't schedule them. And then we just let EC2 scale up and down. Is there an easy way to kind of apply the same scaling rules for ECS and EC2? Or do we have to just do it properly and configure them the same things in 2 different places?
So I always kept it as 2 separate sets of rules because I wanted to do this specific service level auto scaling because I wanted different requirements for each service. And then I have my cluster level auto scaling rules that took care of the cluster itself. I do not know of a more elegant way to take results of service scaling measures as inputs other than doing a custom CloudWatch metric that watch for the event to say, if you've tried to schedule this task and you can't, then scale the cluster up. but I've always scaled my clusters separately because they didn't feel like they went together for me.
Yeah.
But
I think generally most people scale those separately, hence they're separated out in the AWS platform. If you do have the requirement to scale both at the same time, then yeah, I think ultimately that's something that will need to be configured on both sides, the application auto-scaling and the instance auto-scaling, yeah. There's another repo linked from Nathan Peck's, like Awesome ECS, that has a more advanced auto-scaling, like scale in, scale out, based on Lambda there. It's quite cool, it's quite flexible. Might be worth checking out.
it's worth saying that before ECS did native auto scaling, so Nathan and I worked together before this also, and we wrote something in Lambda and Route 53 to handle that. And then we also had something to handle like the socket connections where we needed SSL to terminate through Nginx on the actual container. But that's probably not Amazon information security approved, so we're possibly not going to say that one on Twitch. But these are all possible. I actually think Lambda is that if you're not happy with the built-in one, writing something custom in Lambda is totally the way to go.
Does ECS support non-ephemeral storage?
Non-ephemeral storage meaning like a volume mounted or EFS? EFS?
So EFS is normally the go-to option. I mean, ultimately, the architectural advice there should normally be try and get the state outside of your containers anyway, right? Think about things like S3, think about Dynamo, RDS, etc., to move that state out. Ultimately, it's going to give you a better architecture, more scalable independently, etc. That said, there are always some like occasions where you're running some third-party app or something where you need persistent storage in a file system form. EFS is the best option for that today.
If you're looking for some people talking about doing that on Amazon, Arun Gupta, who's on the open source team, has written a couple of blog posts about doing persistent storage. So I've never wanted to keep my storage that way, but there are definitely people out there doing it, and EFS is probably the best answer.
Any other questions? Okay.
Maybe